All right, we have started recording, and the last time we finished looking at the real zeros of a polynomials. Okay, so here's the synopsis of what we have covered. As far as a rational function in general is in the form of n of x over d of x. To graph a rational function, just like any other function, we need intercepts. In addition to that, we find asymptotes. Vertical asymptotes, horizontal asymptotes, oblique asymptotes, okay? Then, as far as this section is concerned, I mentioned the division algorithm and what it means, but more importantly, understanding the remainder and the factor theorem, okay? Basically, they are the same. Remainder theorem says if you are dividing by x minus k or a or c, just evaluate the function at that point, okay? And if it's any number, that's your remainder. If it happened to be a zero, it becomes a factor. For example, when we looked at this example, we just plugged in. Whenever the remainder is zero, that means it's a factor. We looked at this, and I mentioned synthetic division. Remember, there are three ways to find the remainder. You can do it by long division, synthetic division, or the remainder theorem. Generally speaking, the fastest and the easiest is the remainder theorem. Does that make sense? Rational zeros, okay. To have a better understanding of that, we looked at a simple example. The idea behind the rational zero is when you write a polynomial in descending order, you look at two pieces of information, a sub zero, the constant, and a sub n, the leading coefficient, okay? And you find factors for each case, and you divide the factors of a sub zero over a sub n. So what are those? Those are possible rational solutions. It doesn't mean they are all solutions. Those are just possible solutions, okay? And so all you have to do is check them out. And as long as we get one or two right, we can take care of the rest. Because this is of degree 3, if we get one of them right, the rest of it can be done by factoring or even the quadratic formula. Okay? That makes sense, everyone? Then we looked at the number of zeros and Descartes' rule of sign, which means we looked at f of x and how many sign changes. Then we evaluated f of negative x and we looked at how many sign changes. All right. This is the one we skipped, I believe, because I thought we don't need to worry about this. Did we do this question? Okay, why don't we take a moment, okay, and do this. Okay, class. So everybody remembers how we do that. First of all, we are looking at this and we know this is of degree 4, therefore we expect 4 zeros. Remember, when we say 4 zeros, that's the maximum number of zeros and they don't have to be distinct. And some of them may not even be rational, maybe complex, otherwise you name it. And so with that being the case, we have an idea of what's going on. So what I want you to do, factors of a sub 0 over factors of a sub n, okay? So first the degree is obviously 4. So we have probably 4 zeros. Now, what you want to do, you want to come up with those factors. So let's give everybody a moment. Look at a sub n and a sub 0 and write factors of those. I mean, if you look at the top right, we do have the formula, right, class? So you should be able to figure out what's going on. Right here. Okay? Just for the sake of argument, what is your a sub 0?
0.
9. A sub 0 is 9. okay? And a sub 0 is the constant, remember that, okay, class? A sub, and look at this one. This is called the leading term. 2x to the power of 4 is called the leading term. So a sub n, in this case, means a sub 4. Why a sub 4? Because the degree is 4. Are you with me? And that one is equal to number 2. So when you factor out each one, you know what you get. So let's talk about number 9. What are the factors? Plus minus 1, plus minus 3, plus minus 9. Does that make sense? And what about a sub n, which is 2? Plus minus 1, plus minus 2. Now you are going to divide the prior numbers, the previous numbers mentioned, over plus minus 1. That gives you the same numbers. And now you're going to divide those numbers by plus minus 2. And that creates plus minus 1/2, plus minus 3/2, and plus minus 9/2. Is everybody okay with that? All right. So what I'd like you to do, let's just try a couple of easy numbers. Let's try 1 and negative 1. Okay, class? Sounds good? So plug in 1, see if you get 0. Plug in negative 1, see if you get 0. So let's see what happens. You can do it by any method. Obviously, long division, synthetic division, remainder theorem, it's absolutely up to you. So do those and see what you get. When you plug in 1, what do you get? Do you get 0? When you plug in negative 1, do you get 0? Okay, so if that is the case, class, if negative 1 results in 0, can anybody tell me what should be our next step? Remember, we want to find all the zeros. We want to write this in factored form if need be. So what should be our next step? Anyone? To write it in factored form, first you got to divide by x plus 1 to see what is your quotient, and then work on factoring that piece. Isn't that the case? And then you can plug in again into that negative 1 again. Maybe negative 1 is a factor of that, which means you have x plus 1 to the second power, just as an example. Okay, so first you divide, you come up with the new answer, the new quotient, and then you try the same number on that, because we may have a multiplicity of who knows what. Yes? Does that make sense? So I'm assuming everybody can do the synthetic division. And this is what we get. Is everybody okay with that? Everybody can do the synthetic division? So can you tell me, therefore, so far, the function f of x is equal to the product of what? Give me two things. Now that you have the synthetic division, you can write f of x equals x plus 1 times what? Come on, you know the meaning of synthetic division, right?
2x cubed, 11x squared, 18x.
Thank you. That sounds perfect. We are not finished, but up to here, is everybody following? Good. So now we went from exponent 4, degree 4 to degree 3. Now the second piece is of degree 3, and we need to handle it. Is that right? Does it make sense, everybody? Now the second piece, all of those we can try on it. In fact, you can try the negative 1 again. You follow what I'm saying? Because again, we may have x plus 1 to the power of who knows? X plus 1 squared, maybe x plus 1 cubed, maybe even x plus 1 to the 4th. So you can try it again. Many times it does happen. So try -1. What happens? Everybody knows we are trying the -1 on which one, right? The second piece. Okay, the second piece. And so now what do we get? Do we get 0?
Yeah.
Therefore, x plus 1 squared is a factor. Is everybody with me so far? So, what do you think we should do therefore? What should be our next step? What would you do? Exactly. You have two choices, class. You can try other numbers, you get lucky, you have a factor. Other numbers you have, or just do the synthetic division. When you do the synthetic division again, the resulting function is of degree 2, isn't it? And degree 2, we can even factor. So let's give everybody a minute before I put up the synthetic division to make sure you remember how to do the synthetic division. That sounds good? Okay, give it a shot. Synthetic division on 2x cubed plus 11x squared plus 18x plus 9, which means you're going to write 2, 11, 18, and 9, and you're going to put -1 and work on it and see what you get. Okay. Everybody has the synthetic done, right? Okay, synthetic division results in that. Sounds good? Therefore, we are looking at x plus 1 quantity squared times what?
2x squared plus 9x plus 9.
By any means. How about factoring? Try to factor that and understand, class. 2x squared, 2 is a prime number, it's x and 2, so it's really not too bad. Are you with me? See if it works out or not. Students online, everybody is doing good and everybody can hear me.
Yes.
Excellent. All right. So we are factoring the second piece, 2x squared. So you open up a couple of parentheses. Right, class? And what do you want? You want two numbers, the product is 9, and somehow the middle term should work. So that works. So we get x plus 1 quantity squared times x plus 3 times 2x plus 3. Okay? So what are the real zeros for this function? There are 4 of them. -1 has a multiplicity 2. That's one of them with multiplicity 2, in essence 2. Are you with me? What is the next one? -3, and the last one? And we are done. Any questions up to here? All right. So now, I hope it's straightforward. Everybody? So this is just to refresh your memory about what we did last time. Finally, what if we have this question? What is the solution to this equation, everybody, when you set it equal to 0? Anyone? It's an obvious answer. The answer is looking at you. Just all you have to do is say, oh, okay, I see you. That's all you have to do. That's it. Yeah. When you set it equal to 0, you get those because those are the that's the same function in factored format, isn't it? So what is the solution to the equation? What are the zeros of the function? The x-intercepts, if you want to graph them, all of them mean the same thing. If we are looking at the x-intercepts, of course, we put them in pairs. Sounds good, everybody? All right, we're going to move on. Are we ready for that?
How did we establish that one had a multiplicity of 2?
Because we divided by x plus 1 again and again and again. How many times did we do that? Okay, as long as you can, and you know, you may be able to do it even one more time. You know, not in this case, it didn't happen, but it could. So the question was, how do we know the multiplicity of -1 is 2? Because we divided by x plus 1 using synthetic division 2 times. Make sense? Everyone? We're going to move on. All right, let's do it. So we are looking at a theorem that discusses bound on zeros theorem. What it means is that, is there a way to find the largest possible zero on the positive side? And is there a way to find the smallest negative number? And the purpose of that, okay, if we have so many zeros from the rational zero theorem, can we cut it into less numbers and make it more manageable? That's the concept. Is everybody with me? All right, so that's why we have this bound theorem. So if C is larger than 0, C is a number, is a positive number. And you do the synthetic division using that C, okay? And the resulting row, which gives you the quotient, it's all non-negative. That is a bound, okay? Now, it's important to know if, for example, number 4 happened to be a bound, then so is any number larger than that. Are you with me? But we are interested in the smallest number because we don't want to go up. If 4 is the number of interest, what does it mean? Well, a bunch of rational zeros. Some of them were large, like 9 maybe. Do you remember that? Or 12 in the previous examples. I don't have to waste my time checking those numbers, okay? Same thing. If you find the bound on the other side, on the negative side, and for example, the bound is -2, then you don't have to even check -3. Are you with me? That's the idea. Sounds good? All right. So we have this theorem. Now, finding the bound is not easy. I want you to know that. It's just, in order to find it, you just have to pick up the smallest positive number and try it, and then go up and up until it stops, okay? And the largest negative number and do that. But generally speaking, they give you numbers and say, try, and is this a upper bound or is this a lower bound? And again, maybe difficult to understand it at this point, but let's make it nice and easy by looking at a very simple example. And the question is, given the function p of x, okay, show that no real zero is greater than 3. What does it mean? That means establish that number 3 is an upper bound. And the establishment is very simple. Do synthetic division, class, and observe. That's all you're doing. You know how to do the synthetic division. Okay, let's do the synthetic division. We need to use what numbers? 2, -5, 3, and 1. They are in descending order. What is missing? Now something is missing. X to the power of 2 is missing, right? So you have to replace that with 0. In other words, 2, -5, 0. Okay? 3 and 1. When we are trying number 3, that means we are dividing in essence by x minus 3. Am I right? Let's give everybody a moment to do the synthetic division on that. What do you get? So in other words, you want to do this class, okay? Do the synthetic division. You know what that means, right? So we are putting them in order. 2, -5, 0, x squared. Therefore 0, 3, 1. And all you have to do, come up with the next row. That's all you have to do, class. So what is the next row? And you're more than welcome to work together, okay? Anybody has the next row for us? Obviously, we drop the 2, and then what happens? Yeah, multiplied by 3, added to -5 gives you 1. Okay, continue.
You have 3 to 0, you get 3. Add 3, you get 12, and you get 37.
That's what you mean. Sounds good to everybody? Everybody can come up with that, yes? Class. Last row. All of them non-negative. By the way, even if you have a 0 is okay. Are you with me? All of them are positive. So is number 3 an upper bound? Yes. So the answer to part A is yes. Okay. No real 0 is greater than number 3. That's the meaning of it. Never mind part B. I want to make sure we got part A. Do we understand the question? Look at the theorem and what it tells us. The theorem says, if you have a number, which is a positive number, and you do the synthetic division, and the resulting row, which is the quotient row, right? And the last one is a remainder. It's non-negative, that is an upper bound. Of course, if number 3 is an upper bound, so is number 5, so is number 10. We don't care for larger numbers. We are hoping to make this smaller because we want to, make this more manageable. Is everybody okay with that? All rows, okay, the whole row must consist of positive numbers only. Now, all are non-negative. The answer is yes. Okay. Now, what do you think we should do with part B? We're going to repeat exactly the same thing. Okay, class? Instead of number 3, you're working on, instead of that, you're working on -1. Go ahead and do that. All right, so we are working on our synthetic division. The first number 2 drops, okay? And we multiply it by -1. becomes -2. We add it to -5 and we get -7. So we move on. Agreed? As long as you can get one of them, I'm assuming you can get the rest because the same process continues. So here's the final answer and the last row. We are okay with that, everybody. What do we notice? They are alternating in sign, aren't they? And that's also a theorem on bound. If the resulting row alternates, that is also a bound on the negative side. Negative side, that means a lower bound. So we established that -1 is a lower bound. So if that is a lower bound, we don't have to check -2 or -3 or any other number that is, less than that. Is everybody okay with the concept? We're going to move on. So we have lower bound, upper bound, we have the rational zero theorem, we have Descartes' rule of sign. There's a lot to, handle here. Now, finding the bounds may not be easy. So the same thing I do for the exam. I give you an example and I say, okay, is this upper bound? You say yes or no by going through the process. I'm not going to ask you to find the upper bound. Are you with me? But the process is, if they tell you to find the upper bound, you really have to start with the smallest positive number and move up and see what happens. That's the concept. Done?
For the lower bound, if there is instead of like say it was 7, it was 2, -7, and 0, would that still be considered alternating?
If the first one is negative and the second one is positive and it continues it. Alternating, that means doesn't matter what's the first one. The next one now, opposite side. You start with positive, the next one must be negative. But has to be alternating in this case.
So what I'm asking is, would 0 fall under?
Yes. Zero, class. 0 is whatever you want it to be. Okay? If you need a negative number, you assume it's negative. If you need a positive number, you assume it's positive, and that works out. If you happen to have a 0 for any of them, that works out as the sign that you need. Okay? For example, in this one, any of them is 0 is good. You consider it to be positive. Over here, if it's here, you consider it positive. Here, consider it negative. Here, consider it positive. So if you have a 0, you can go either way. You choose that. That's the method. So we have the answer. Everybody okay with that? Are we ready for the next one? All right. Find the integer upper and lower bound on 0. So I won't be asking you in this way because, again, that does take some time to do it. But at the very least, let's give it a shot, see how this works. The first thing that you can do, and you can answer that in a split second, is that first and foremost, what are possible zeros, rational zeros? By now, you are familiar with the rational zero theorem, and you should figure it out in no time. So first, give me the answer for that, and then we take it from there. All right. The same thing, factors of a sub 0 over factors of a sub n. A sub 0 is what number? Negative 36. A sub 1 or a sub 4, because the degree is 4, are you with me? Is equal to 1. So what are the possible answers? Many, right? All the factors of 36 will do the job, or negative 36, which is plus minus 1, plus minus 2, plus minus 3, plus minus 4, and you go all the way plus minus 6, plus minus 9, right? Plus minus 12, plus minus 36, all of the above. And so you divide it and you end up with those. So you have a lot of numbers to check. The process is upper bound, start with the smallest positive integer and move up. For example, what is the smallest positive number here? So the process is we try 1. It works, we are done. That's the upper bound. What do I mean it works? That means we look at the last row. Doesn't work. We move on with number 2, number 3, number 4, and we continue number 6 and so forth. Are you with me? On the other hand, we do the same thing with the negative side. The largest negative number is negative 1. You don't start with negative 9, okay? So you start with negative 1 and do the math. Does that make sense? Okay. With that being the case, just take a look at what happens. So this is the concept. If you write those, let's say you have done the work, okay, class? And so when you divide, those are the coefficients and those are the answers. So you want to know what happens now. You've done the math, okay, and you want to make a decision. The numbers that are used as R or K are the first column. In other words, the first one is meaning we checked number 1. Are you with me? The second one says we checked number 2 and 3, and the rest of them, on the rest of the numbers on the right side are the last row of your synthetic division. Are you with me? Of course, it's been done because I don't want to waste time. You can do it one by one. We don't want to go through that. But I want to make sure everybody understands what that table is. The first column are those possible rational zeros. Okay? The rest of them are the theorem that was done. So with that, with synthetic division. With that being the case, you have to look at the one that gives you all positive for the positive numbers, and for the negative, the alternating, okay? So notice what happens here, okay? Upper bound is 3. Why is that? Because look at that. In front of 3, and you have to look at 1 and 2 and 3 only. We're talking about positive, okay? Upper bound. 1 is not the upper bound. Why not? Because we have some negative there. Are you with me? 2, everybody understands. When we look at 1, okay, when we are dividing by 1, this is the answer, okay? Synthetic division. When we are dividing by 2 is the next one, and here's for number 3. Okay, this is the row that all of them are. It so happened, it is a factor also, which is x minus 3 is a factor. Now, if you're trying any other number, then you're not going to go up. You're going to go down to 2 and 1. So what does it mean? It makes life easier, doesn't it? Everybody's following what I'm saying? Okay. That's as far as the upper bound. Now, as far as the lower bound is concerned, do you see what happens, for example, with negative 1? Let's look at negative 1 just as an example. Okay, didn't work. I messed it up. Isn't that the case? So if I look at negative 1 as an example, is this alternating? The first number is 1. The second one is negative 1. The third one is negative 4. It doesn't alternate, does it? So that's why it's not an answer. However, this one does. And that's why -3 is your lower bound. So it makes life easy now, class. All you have to do, if -3 is the lower bound, the other ones are -2 and -1 that you have to check. By the way, it has been already checked here and there are no solutions, okay? So you don't have to go look at -4 or -6 or anything smaller than that. Sounds good? Is everybody following what's the meaning of a lower and upper bound? All right, we're gonna go to the last page. Any questions?
So, just so I understand, does that mean that only the middle row is upper bound?
Number 3 represents an upper bound.
And it's only that one, right? Everything
Yeah.
else, every other row is technically lower bound. So like a positive negative in it?
See, when you find a positive number such as 3, where the resulting row, okay, through the synthetic division, which represents the quotient and the remainder, in this case, the remainder is 0, they are all non-negative. That's your upper bound. What is the meaning of upper bound? There is no other number larger than 3 that will be the 0 of this function. Okay, take a look at factors, class. Take a look at possible rational zeros. Okay, let's go with positive numbers. What do we have? 1, 2, 3, and then it becomes larger, right? 4, I'm not going to check it anymore. And that's the idea. I'm not going to check the rest of them. 4, 6, 9, 12, 18. I don't need to bother with any of those. That's the idea behind the upper bound.
I get that. What I'm asking is, in this chart that you have,
Yes.
based on what you said earlier, does that mean
Number 3 is the upper bound, the only upper bound.
that's the only one?
The only upper
That's
bound.
just one.
Because the other 2, the problem with number 2, let's say number 2 had a resulting synthetic division that all of them were non-negative, then 2 would be the upper bound, and you don't even have to check. And remember, when you're checking, you really are checking with 1 first, 2, 3. 3 happen to give you the answer, and you don't go any further. Not that it gives you the fact, it doesn't have to give you the factor. So I want you to pay attention. On the row that starts with 3, even if the last one is 7, I'm making it up, some positive number, you're done. That's your upper bound. Okay, we are not actually getting to the factors. We want to make sure that we have the upper bound.
So like,
Go ahead.
pretend if we use 3 and the remainder is like a positive number. So that's the,
That is still your upper bound, as I said. If number 3 is used and the remainder is anything other than 0 but positive, it is still the same answer. Number 3 is the upper bound.
Is that correct?
Is it wrong?
I think it is. I don't know, I could be wrong, but I just tried plugging in 3 to the formula. And it didn't work. I got enough different numbers.
Okay, 3 to the power of 4, it may be, is 81, isn't it? So 3 doesn't do the job. Let's see. 3 to the power of 4 is 81 minus 5 times 3 cubed minus 36. And that is true. It's not 0 at the end. Okay? The remainder is wrong. The remainder is wrong. You're right. Okay? You can check that. Okay? But what was the remainder? The remainder becomes negative, isn't it there? Is that?
Negative 90, plug in 3.
Okay, negative 9? Negative 90. Okay, so this is wrong and 3 is not. So you have to check with 4. Class, you have to check with 4, you have to check with 6. I hope you read. Did you? Go ahead. Did you want to say something? Okay. So, is everybody following the process? This happened not to be the, I mean, so there is an error involved here, but is everybody following the process? So you can do number 4 and see what happens. I think 4 gives you negative also. By looking at it, I can see that 4 gives you negative. Okay. Then you can try 6 and so on and so forth, okay? So that happened to be wrong, okay? But as I mentioned, the process hopefully is understood. So what I'd like you to do, make sure you try other numbers such as 4, and then the next number is 6, okay? So do that, see what you come up with. You have to do the synthetic division, which means you use 1, -5, 0, 0, negative, just as an example. And we really need to move on. Just as an example, and 4 doesn't do it. I can see already, but what you put in is 1, -5, 0, 0, -36. Everybody can see that? This is how you do the, now you do it with 4, you come up with the answer. You do it with 6, you come up with the answer, and you figure out. In fact, why don't we just quickly do that? On that side, some people are working on 4, right? Can somebody work on 6 on this side of the class? Somebody put number 6 and work it out. What do you get?
We get 1, 1, 6, 36, and 1.
Okay, so if we change this to number 6, we end up with one more time. 1,
1, 6, 36.
so that means what, everybody? Number 6 is the upper bound, therefore. So I believe number 4 doesn't do that for me. Okay, so this is wrong. All right, sounds good. Everybody, let's see if we can, we have it. So doing number 6, that's what we get. All right, ready for the next one? All right, here's a very important theorem. You'll revisit that in calculus. We discussed that in calculus also. It's called short IVT, the intermediate value theorem. The intermediate value theorem says, if we happen to have a continuous function, and that's the key, from A to B, one end is A, giving us f of A as the y coordinate. One end is B, giving us f of B as the y coordinate. Since the function is continuous, it will cover every point from A to B on the x-axis. It must cover every point along the y-axis from f of A to f of B, because it's continuous. Does that make sense? So with that being the case, if one of them happened to be negative, doesn't matter which side, and one of them happened to be positive, it must cross the x-axis. It must have y value equal to 0. Is everybody following that? And that's all there is to it. So for example, if f of x is x to the power of 5 minus x cubed minus 1, we want to show that this function has a 0 between 1 and 2. And by the way, when you show that, it means it has at least 1 0, by the way. It could be that it has more. So all you have to do, plug in 1 and plug in 2. If they have different signs, that's a proof. So go over that. Plug in 1, plug in 2. Let's find out what we have, class. Go ahead. Evaluate when you plug in 1. I think when you plug in 1, it's very simple. 1 to the power of 5 minus 1 cubed. They cancel each other, just minus 1. right? 2 to the power of 5, 32, right? Minus 2 cubed, it's minus 8. So that means 24. Minus 1 is 23. That sounds good? Everybody can do that? So what does it mean? Yes, we just showed that this has a 0 between 1 and 2. Why is that? You got to mention f of x is a polynomial of degree 5 and therefore it's continuous everywhere. By continuous everywhere, we mean from negative to positive infinity. Therefore, it's continuous from 1 to 2. And because the two numbers are different, by IVT, you can write it short for me, that's fine. Yes, it has at least 1 0 in between. I think everybody is clear as to what happened with 11A. Let's give everybody a chance to do 11B. So you got to evaluate it at 2, you got to evaluate it at 3 and make a decision. Go ahead. So when you plug in 2, you get 2 cubed, 8 minus 2 times 2 squared is also 8. They cancel each other. Minus 2 and 1 is negative 1. Agreed? When you plug in 2, you get negative 1. Does that make sense? What happens when you plug in positive 3? Okay, 3 cubed minus 2 times 3 squared minus, okay, very good. So that's what we get. Same thing. F of x is a polynomial of degree 3. Therefore, it's continuous from negative to positive infinity, and it's continuous from 2 to 3 because the two numbers, okay, are different in sign. Then it has at least 1 0 in between. Sounds good? All right, let's continue a few more minutes before we take a break. And we are going to go to the next PowerPoint. Okay. So is everybody done with this? All right, so we are looking at complex zeros. So we covered previous sections and the synopsis of them are here. And this last section that we looked at, real zeros of a polynomial, understanding the remainder theorem. Okay, the factor theorem, IVT, upper bound, lower bound, okay, all of the above. Now we are adding more stuff. So when we go to the next section, class, all right.
What is
Yes,
CTS and IVT?
continuous. CTS stands for continuous and IVT stands for intermediate value theorem. Okay, intermediate value theorem. All right, 4.6 complex zeros. And everybody remembers in general complex zeros. Okay, so let me just put it in slide mode, see if I can do the writing here. Okay, so, okay, nothing, okay. All right, so A plus BI. When we have imaginary solutions, everybody remembers I by definition is square root of -1. Everybody remembers that, right? Okay. So if A plus BI is a solution, so is A minus BI. That's the most important, theorem that we need to know from here because they happen in pair. And so that's the thing. As far as fundamental theorem of algebra is very simple. If you have degree n, you have n zeros. Okay? Not necessarily distinct. Okay? Remember, multiplicity counts. So we are repeating what we have seen. There's really not much brand new here. So the thing that is extremely important, knowing the conjugate, if A plus BI is a solution, so is A minus BI. Okay? So what I want to refresh your memory about here is the following. A couple of things here. I, by definition, is square root of -1. I squared becomes -1, right, class? You remember that? What is I cubed? What is it? -I. Why is that? Because I cubed is I times I squared. Am I right? Do you see it's -I? Yes or no? What is I to the power of 4? That is 1. Does that make sense? So just for the sake of argument, since we are added, therefore, what is I? Let's say to the power of 200. What do you think this is? Okay, it's 1. So how do you know that? Divide the number by 4, everybody. And keep the remainder. If the remainder is 0, the answer is 1. Are you with me? Just for the sake of argument. I to the power of 203. If I divide 203 by 4, the remainder is 3. Agreed? So it's the same as I cubed. And we know I cubed is? That's what happens. All right, the other thing I want to add, everybody remembers A plus B times A minus B is A squared minus B squared. Everybody remembers that, yes? So therefore, what is A plus BI? Times A minus BI. Can anybody tell me? A squared plus B. Plus B squared. Why is it plus B squared? Because when you do minus BI quantity squared, you get minus B squared, I squared, which is plus B squared. Sounds good? Everybody's doing okay with that. Now, I hope we've learned this in intermediate algebra. You've got to remember this stuff, okay? We're gonna move on. All right, class. So here's a question. We want to find a polynomial function with the following zeros, okay? This is the last one we do before we take a break. Quickly, the zeros are 1, another 1, and 4 plus I. Okay, class? So all you have to do, write down, let's say, what the zeros are. And then we move on. What are all the zeros? Can you tell me? There's something missing here. 1 is a 0. And again, 1, that means multiplicity 2. Are you with me? This is degree 4, and we need 4. We are given only 1 more. Beautiful. The conjugate of 4 plus I is also a solution. Agreed? And so you can write it as follows. Now, what comes in front? We call it A, the coefficient. Any number in front will do the job. So if the question is find a function, then you don't bother to write A. Are you with me? But there are infinitely many functions that will do the job if you all you have to do change A to any number of your choice. Okay? But generally speaking, there are infinitely many. So even if you don't write A, I'm okay with that. I want you to know that because the question says find a polynomial. But understand, and if you're looking for A, you don't want to put any other. Either put A or just don't put any number. But put 10 or 1/2 or 10,000 or -8, same answer. Now, all we have to do, multiply them through. The only thing I want you to pay attention is the way we do this product to make life easy. Obviously, x minus 1 times x minus 1 is x minus 1 squared, and everybody knows that, and it's not a big deal, right? So this is not a big deal. X minus 1 squared, and we can do the math, x squared minus 2x plus 1. The way you do this, it's easier to write it as x minus 4 minus I x minus 4 plus I. Why do we write this? Because the brackets, the two brackets, you're looking at a minus bi and a plus bi. The result is a squared plus b squared. So that is x minus 4 squared plus 1 squared. Are you with me so far? Everybody understood? So that's why I mentioned that a plus bi and a minus bi, okay? So again, now that makes it easy. X minus 4 quantity squared, what is that? X squared minus 8x plus 16, right? With that 1 becomes plus 17. Yes? So we are adding 1 and we get plus 17. Now, you just have to multiply x squared by the second parentheses minus 2x by the second parentheses, 1 by the second parentheses, and then collect like terms. It does have some step missing, class, okay? Is everybody following that?